So this force and pressure on the side of a dam sounds reasonable, but let's actually do an example to make it make sense. Okay, so we have a lovely problem right here. We have the lower edge of a dam is defined by the parabola y equals x squared over 16. See the figure below. And assume everything's measured in meters. All right, so we're going to use a coordinate system with y equals 0 at the bottom of the dam. Determine the total force on the dam due to the hydrostatic pressure of the water it is holding back, which extends to the top of the dam. Okay, so one, the water is going all the way to the top of the dam. It says it right there. So we know that the water is filling the dam. All right, I'm going to give myself a little bit of space to work, and then I'm going to write the force down here. Force is the integral from 0 to a, and I know it's 0 to a because they tell us that it's filling. So because it's completely full, this will be 0 to a right there, right, because it's full. And then I know it's rho g h of y, w of y, dy. Okay, so rho and g I actually know right off the bat, and I can figure out some other stuff too, but let's do this. So if water is filling the dam, that means I'm going from 0 down at the bottom to y is equal to 25, right? Right there is letter A for me. So I actually know that I'm going to go from 0 to 25 right here. Clever, huh? Because this is full of water and it's on planet Earth, I know that the rho is 1,000 and the G is 9.8. I can just be done with those two right now, right? So this is because it's H2O. This is because it's Earth. All right, that was the easy stuff. And actually dy is pretty easy too. All right, but I need a formula for h of y, I need a formula for w of y, and then I'll have dy. Okay, h of y is actually not difficult to figure out. So let me take a little wedge here of my dam. So pretend, just look at that strip along the dam. We're going to figure out the pressure on that strip, and then we're just going to add up all the strips. Okay, so that strip, of course, is dy. That's why it was dy. And then I know that if this is the bottom of the dam here, then I know that, here, let me do this. This is a height of y. The whole thing is 25, so this must be 25 minus y. That must be h of y. It's the depth, right? So this is the depth. So I'm going to say it's 25 minus y. Clever, huh? Okay, so then the width. The width is the hardest part. In this case, it's actually not going to be too bad. But just as a warning to you, if it was like a trapezoid like it was on this one, you would use this point here and this point here and find the equation of a line through them. If it's straight, it's actually really easy because it's just linear. This one's not linear, so we have to do a little bit of work. Now, the distance from here to here is the width, right? That's the distance. But I don't have that given to me. What I do have given to me is, sorry, I'm just thinking about my color choices here. I'm going to do it in purple. This piece. I know that piece is x, right? Like I know it. And I know that this curve right here is that relationship right there. So I could solve this for x because x isn't going to do me any good. I can't go put x into here. Moreover, it's not x for the width. Hold that thought. All right, but I know that the distance from the center line out is x, right? Let's take this equation and let's solve it. If y is equal to x squared over 16, then 16y is equal to x squared, and so x is equal to, now it's technically plus or minus the square root of 16y. However, because we're in this positive quadrant, we would only use the positive. So x is equal to 4 square root y, because the square root of 16 is 4. All right, now how did that help me? Well, because that's that, right? So I know that that x right there is 4 square root y. Now that's not the answer. That's not the width. Why not? Well, because the width goes from the left side to the right side. We just found from the 0 to the right side. So the width is W of y is 2 times x, which is 2 times 4 square root y. Because x won't do me any good. You could go put x into here, but it would be wrong because you have to have them all be variables of y. So 2 x's. There's an x on the right and an x on the left, and together, there's 2 of them. They make the width, right? So if I know that this is 4 square root of y, this is negative 4 square root of y, together they make 8 square root of y. That's your width. All right. Right? Now that I'm here, I've got everything I need, right? I can bring out 1,000 times 9.8 times 8, actually. There's 8's a constant. This one's a constant. This one's a constant. So those 3 numbers, I'm actually going to pull them with Desmos and just grab them. Oop, not there. That wasn't it. Oh, Desmos. Oh, forget it. I'm just going to make a Desmos graph. Oh, it was here. I just didn't see it. Okay, so it's 9.8 times 1,000, which we've seen before, but times 8 this time because 8 is a constant. So it's 78,400. Okay, so we have 78,400 out in front. And then it's the integral from 0 to 25. And then what do we have left? This is a y to the 1/2 right here. So if I look at what I've got, I have a 25 times a y to the 1/2, which is 25y to the 1/2, minus a y times a y to the 1/2, which is a y to the 3/2 dy, which is 78,400 times, all right, add 1 to the power, so it'd be 25 times y to the 3/2 and then 2/3 minus 2/5 y to the 5/2. And we're going to take this from 0 to 25. Well, once again, the 0 is irrelevant, right? All we really want to do is put 25 into that thing. So I'm just going to do that with Desmos. So let's see, 25 times 2/3 times 5, or 25 to the 3/2 minus 2/5 times 25 to the 5/2. And that's 833.3, or 2,500 over 3. So 2,500 over 3 divided by 3 times it by 78,400. We'll get a 60, well, that huge number. All right, so let me go back here. So this was 78,000, or 78,400, excuse me, 78,400 times 2,500 over 3, which came to 65333 newtons. And there we go. We are done with chapter 6.